Thank you, Mateo, and thank you all for coming out, both here and in the atmosphere. That was an improvisational thing. Um, no, it's seriously a real honor to be here. It's really weird how life is weird in many ways, but in this particular way, weird in a good way. Because some of this talk, I would have never guessed that back in 2005, somebody in this room happens to be the director of the CCA. I was a starving, no, not starving. I was a postdoc, hoping that one day I might get a job, and really struggling to figure out ideas to work on. And I think this is a very valuable lesson, actually. And I try to apply this to myself now when I deal with students and postdocs. And I had this crazy idea, and I knew the idea was that insane and crazy that if I would have told my colleagues, the other postdocs, I would have not been invited to the reindeer games anymore. Coincidentally, David Spergel was visiting, and he seemed like a really, easygoing person. So I went up to him and I kind of told him this crazy idea. It actually was about the matter-antimatter asymmetry, a problem I was working on in cosmology with someone else who I'll talk about in a second. And anyway, to make a long story short, I was expecting this fancy professor from Princeton, WMAP, co-PI, to say, that's garbage, see you later. And he said, go for it. Sounds interesting. And here I am, 15 years later or something like that, talking about a big core of that idea. And actually another coincidence is actually the mathematics, the core mathematics underlying this, what I'm going to talk about today. The math underlying it concerns Chern-Simons theory, another interesting coincidence. I met Jim Simons in 2011, so that was it wasn't like, I'm some soothsayer or something like that. I was anticipating that. So just interesting coincidences. And in fact, today I'm going to talk about coincidences. I'm going to talk about coincidences that are right and coincidences that are wrong. Okay? So here we go. This talk is intended to be, at the first half, as pedagogical as possible, because I know this is a very intellectually diverse group of audience members. So I'm going to do my best to try to be, some of you will know something about something I'm talking about, okay? But a few of you will know everything I'm talking about, including myself. So first of all, I want to acknowledge the students in my group. So we have two postdoctoral researchers, Gabriel Hersek, who hails from Brooklyn, went to Brooklyn College, Stephen Clark, Tetsuya Daniel, who just joined us from MIT as an undergraduate, my three graduates, Leah Jenks, Michael Toomey, and some undergraduates that I work with throughout the year. And I even have a high school student that works with me in the summertime. And also, in terms of, what I'm going to talk about today actually represents about a decade of a particular thread of research that I've been involved with. And so these are some of the players in my court. My former postdoc, Evan McDonough, who is now at the University of Chicago, KICP, working with Rocky Kolb and Wayne Hu. My former postdoc advisor, Michael Peskin, Mohammed Sheikh Jabari, we were pals together as postdoc when we started working on this. And many of you, I guess, can guess the person there to the left, well, all decked out at the Breakthrough Prize, David Spergel. So first I'm going to do is kind of give the big picture, the blazing view of modern cosmology, and kind of point at an issue that concerns us all. No matter where in astrophysics you live, this issue will concern you all. Then I'll talk about the role of gravitational waves as a physical processing thing, not just as a thing that you might want to observe, but something that does something in the world. Gravitational waves, I will use gravity waves. I know it corresponds to waves on water, but for now, I'm a bit lazy. All right, so then I'll talk about one of the key things that we're after here, which is this. Basically, why is there stuff in the universe rather than nothing? When I say stuff, I mean the visible matter around us, okay? That's one way of saying this. I'll be more precise about that. And then I'm going to talk about a mechanism that was developed by my colleagues and I that basically uses the physics of cosmic inflation to actually do the baryon asymmetry. Now, for many of you inflationary experts there, you should say impossible, because for obvious reasons, and we'll deal with that. And then I'm going to end with this issue of the genesis of dark matter, whatever it may be. It'll turn out that the Chern-Simons, the mathematics of Chern-Simons theory, constrains actually what that theory looks like, rather than being ad hoc. And then we'll talk about future directions. So let's begin. All right, it begins with Albert Einstein. His discovery of general relativity basically states that, matter and energy tells space-time how to bend, and space-time, right, tells matter how to move, right? This dynamic interplay between the curvature of space and time and matter and energy. And we can say, what are the consequences for cosmology? Well, cosmology stuff in the universe doesn't make space-time bend by making it expand. And so, before we go there, it's not just enough to just specify that general relativity with stuff in the universe does one thing. You need principles. And one of the most amazing things I remember learning when I started off as a grad student was my advisor, Robert Brandenburger, telling him, this basically is his bread and butter slide. I've written myself, okay, but basically says, look, what's amazing about cosmology, at least, is that you can state 3 principles. And with these 3 principles and general relativity, you get a prediction that pretty much predicts most of what we see out there, with just 3 principles. What are these? Cosmological principle, which states that on the largest scales observable, the universe is homogeneous and isotropic. Think about an idealized surface of a sphere. The Hubble expansion law, the observations that galaxies recede away, the velocity proportional to their distance from the observer. The third is the theory of general relativity. These 3 principles that come together have a predictive mathematical solution, which is the expanding universe. And the takeaway here is that I want you to think of each galaxy pinned to the surface of this balloon. And if this balloon is expanded at some constant rate, even though the galaxies are pinned and not moving, they appear to be moving relative to each other. The further the galaxies are away, the further these little dots are away from each other, they move away faster. And this is a prediction of the expanding universe, which is the Hubble expansion law. So that's a prediction of the theory that presents mathematical solutions that agree with observations. The other thing that concerns us, of course, and this is, I call this the CCA universe, right? Which is basically, if we look at all the way to those little dots there, blue and what have you, that corresponds to some primordial state in the universe at roughly 14 billion years ago. And what we're looking at there is the growth of structure into the large-scale structure that we see today of galaxies and dark matter and all that stuff. We'll talk about that in a second. And standard cosmology, with the cosmological principle, does not explain that phenomenon. Okay? We need something else, meaning if we go back to the early universe that was hot and dense, and the universe was filled with equal matter and radiation, if that is completely homogeneous and isotropic, then you can't basically use gravity to grow structures. You need something else. And here we're looking at post-WMAP, Planck satellite data. And what we're looking at here is the anisotropies of the cosmic microwave background radiation, which is a time in the universe's past where it was filled with radiation, a plasma filled with radiation and electrons and soups of quarks and all that good stuff. Now, the different colors correspond to peaks and troughs in the gravitational potential. So clearly, these tiny undulations, okay, about this homogeneous and isotropic background where the radiation has the same temperature. Okay, so I want you to think of an ocean, and the ocean basically, the height of that ocean, is the same everywhere, and that's the temperature of the cosmic microwave background radiation, which is homogeneous and isotropic, in line with the cosmological principle. But we have tiny undulations, 10,000th of a time smaller than that average, and those undulations are the things that we now know to grow into the stars in the galaxies that we see today. And there's tons of complicated physics, some of which we still don't understand. I see Dr. Somerville is here. I mean, galaxy formation. I'm here to learn about that stuff, okay? So there's a lot of stuff going on, but what we do know is that this is the seeds of the structure, okay? And the question now remains, so what? And so if we look at, this is actually the W map. David, I'm not going to tell you what year, because I don't know what year this was.
That is the 5-year data.
Okay, the 5-year W map data. Thank you, David.
It's like 2000, right?
Yeah.
2007 data.
2007.
And so what we're looking at here is on the top, we have these peaks and the valleys. And if I want you to now think about sound, okay? Each height and right of those peaks corresponds to the volume. And so of how high the sound is here, okay, of that wave. Now think of this as sound waves. And if I can represent the height of the sound waves, okay, going from the lowest note to the highest pitch. So this is the low pitch, and this goes up to the highest pitch of that sound wave. And what we find is that there's a sweet spot where there's a resonance, the same thing that makes the flute blow at the fundamental frequency. And that peak is something that Jim Peebles won the Nobel Prize for by predicting that using standard cosmology with the fluctuations. And this is another prediction of the standard cosmology. If you include these oscillations that grow into structure, and that corresponds to the polarization of the photons that come to us. All right, this is a blazing review. This could have been, see, I saw David give a colloquium, and it took David 15 minutes to do that. So, so I'm going really fast. So what? I mean, so you see these peaks, but why should we care about these peaks, aside from the fact that they're really pretty? The first thing I want to also say, these dots here, with error bars here, is the data. And I'm going to talk about something called, I'm leading up to basically the big question, where do these fluctuations come from, or how did they come about? What sourced it? All right? It turns out that the physics for that is not explained by our standard cosmology. We'll need something else called inflationary theory. But the point is that if you play all this game, or what I was saying is that if you take inflationary theory and you process the equations, the red curve is a prediction of inflationary theories for a specific set of parameters. Okay? So we get a beautiful matching between theory and experiment. This is why we say we're in the age of precision cosmology. One of the reasons. So the other thing that I want you to take away is that the relative peaks, if you look at these things, right? The same way an instrument vibrates, it depends on how the makeup of the instrument. So if I have a woodwind versus a metallic instrument like my saxophone, they will vibrate. The material will vibrate differently for the same note. So I can deduce the size, the shape of my instrument, as well as the material makeup of that instrument. The same physics of sound applies here. What we find is that these relative peaks give us information about the makeup of the universe. And from that, we can deduce that, that basically the energy budget of the universe, and this is plus or minus this thing called the Hubble tension. I'm not going to talk about that today. That roughly 70% of this energy, of the energy in the universe, is not visible to us. It's unknown. We call it dark energy. And we see that we make up roughly 0.5%. And of course, there's this thing called dark matter, which I'll talk about later on. But what I want you to keep in mind here is that both the dark matter, and I believe WMAP was the first to make this observation in CMB, which deduced not only the dark matter density, but the baryon density, so we can weigh, right, the amount of baryons, the amount of visible matter, and the amount of dark matter using the cosmic microwave background, not only contemporary observations today in galaxies and clusters of galaxies. All right, so who ordered that? And so I'm now going to talk about inflation. I'll say a few words about what inflation is. So we know the universe is expanding now, and the basic point of inflation is actually the idea is simple. The idea is not simple because I wouldn't have come up with it. But the basic idea is the universe is expanding today. You go back to the CMB, there's this weird thing. When we look at, using CMB telescopes at the temperature, what we find is that we see that the temperature, so we look in one direction in the sky, traced back to 14 billion years. So this picture here, this surface, I guess I'll just point. This surface down here corresponds to the temperature of the cosmic microwave background radiation. And this is us today looking back at one antipodal point in the sky, 14 billion years, and another antipodal point. And what we find is that it will take that light with the same exact property for thermal equilibrium, meaning that they should have interacted with each other. It would take that light longer than the observed age of the universe. So there's an internal inconsistency with our theory. In other words, we have to go beyond local physics, and you'll see in a second, the physics that we're using to actually talk about the structure turn out to be local quantum field theory. So there's a problem here, and these little cones represent light cones that correspond to the photons, range of causal interaction, and what we find is that they're out of each other's causal interaction, even though they appear to have the same temperature, right, which should bother you. So Alan Hughes came and solved that problem by basically saying, actually, if you go to some earlier time in the universe, 10 to the minus 33 seconds, okay? After t is equal to 0, I'm not going to talk about t is equal to 0 today. If you go to that time, and you just say you have a tiny little patch of space where everything is actually interacting. Something is interacting in equilibrium, not equilibrium, but something is in causal contact. If that thing underwent some explosive exponential growth, right, then it could match the surface, and everything actually was already in that horizon. And we say, well, okay, so what? So inflation does solve this thing called a horizon problem, but you get a bonus out of this. But before I go on, I just want to, kind of now step back and summarize what we now know about cosmology. We have the Planck epoch, and we didn't talk about that. All this stuff, right? Stagflation, emergency stop, present day. And we have the future cosmological development handed over by J.J. Abrams. And we don't know what the future will have, but we could talk about today and the past. I mean, maybe Spider-Man, maybe it's, some other sci-fi movie. And let me first then move on and say, what I'm going to talk about in terms of the research engaged here, so far I'm reviewing, might seem to be a little bit like sci-fi. And that's why I use the word in my title, story, because as theorists, we tell stories. And we try to make the best story that we can possibly make, and then we hope to talk to our friends who go look for things, who make observations, who do experiments, and we hope that our story is partially true. It is not fake news. Okay. So I want to go back to my mentor, Alan Guth. As I said, Guth, you're the man with the plan. Okay, so what makes inflation happen? But what is this? I want to talk a little bit about the dynamics of inflation, about the gymnastics of inflation, because it's going to come to help us talk about this matter-antimatter asymmetry. The first thing to realize is that inflation really was born, right, out of particle physics as well. Guth was trying to solve something called the magnetic monopole problem, having to do with grand unified theories. And in trying to solve that problem, he realized that you needed another field in nature. Another fundamental spin zero field, scalar field, does the job. And of course, it's good to know that we discovered, not we, but the community discovered the Higgs boson, which is thought to be a fundamental scalar field. So maybe there's another one out there. Maybe it's a complex, part of something like a Higgs called an axion. But the basic idea, though, generically, is quite straightforward. What you need, I want you to now think about a ball rolling down a hill. Okay, now if the ball had no friction, well, rolling friction, it'll just roll down the hill under usual gravity, right? But imagine I put a little bit of Velcro, some kind of Velcro. The ball might just, because of this extra dynamic friction, will roll down slow. Okay. So what inflation is the following picture. This field, think about it as a ball, right? It's not really a ball, it's a distribution of energy in space-time. But what happens is that the amplitude or the height of this field, its value, its loudness, basically slowly rolls down the hill, right? It has that type of physics that basically keeps it, instead of quickly rolling down the hill, slowly rolling down the hill. And that type of friction is basically the Einstein field equation. The dynamics of the space-time sees that slow rolling as basically a particular form of potential energy that has negative pressure. Negative pressure is different than positive pressure. I pull a rubber band, it pulls me back. Negative pressure, I pull a rubber band, it goes out even further. Kind of a form of repulsive gravity. So what inflation does with this inflaton field, the scalar field I'm showing, this phi, it's being stuck and fully dominated by this potential energy. And remember, the kinetic energy is nearly vanishing. That basically makes the universe accelerate up exponentially. All right? That's one way of thinking about it. And now what I want to say is that part of inflation of this inflaton is a part that controls a homogeneous and isotropic part of the space-time. It's making, right, the universe expand. However, the question here is, how do we generate the seeds of these structures? How do we generate, right, the perturbations, the undulations that become the stuff in the cosmic microwave background? And what we need here, and this is a bonus, the inflaton has a quantum part, right? The inflaton field has basically the part that's rolling, and it also has a part that we call a quantum fluctuation. And this quantum fluctuation is the thing, there's quantum magic going on, and I want to talk about that quantum magic. So the basic idea here is that this is time, the universe is inflating along from here. So let's look at this pocket of time here where inflation happens. To the right here, we're looking at a characteristic oscillation, a characteristic wavelength with some size. And this wavelength is basically living within the region of causal contact. It is generated causally. And what inflation does then, because inflation is stretching space, it stretches that wavelength. But it does something more than that. It stretches the wavelength of the quantum fluctuation, but it also does two more things. That's quantum magic. It basically creates something called quantum squeezing for all these different oscillations. So it makes these waves all coherent. It's like all of the violinists playing the same note at the same time, or many notes at the same time. And it stretches it, and those are the things that come back in to generate the structures. So it takes this microscopic stuff, subatomic size, situation, and makes as the universe gets big, those things grow, those waves grow, and they become the seeds of structure. So inflation does this as a prediction. It didn't do this, this came after Guth, realized that inflation could solve the monopole problem and the horizon problem. Okay, so inflation provides us just with a causal and predictive mechanism for generating the primordial perturbations required for galaxies, clusters, and superclusters. I'm saying big words, obviously, I'm saying things for which I know not. I'm talking about, galaxies, clusters, and superclusters. However, I want to say something just as for those of you who are like Stephon is saying a bunch of gobbledygook because we know we don't really have yet a full theory of inflation, I want to say that that is definitely important work to continue to be doing. You know, one of the reasons why when I was at Stanford was I was working on to try to merge inflation with string theory, for example. And part of the reason why that happens is the very same quantum fluctuations you're using to generate the structure, those quantum fluctuations feed in to the very potential smooth surface the inflaton field was undergoing, rolling down, and spoils that beautiful flatness that you need to keep it slowly rolling. And so, as a result, that points at, you know, the hint that actually inflation might need a UV completion. For those of you interested, look at some early work back in 2000 and some more hardcore stuff by Silverstein and Tom. So, okay, what am I leading up to here? Well, we talked about the structure. We talked about the quantum fluctuations of the inflaton field, but they're quantum fluctuations of space-time itself that have to come along for the ride. And these things are called gravitational waves. So the basic idea here, just to summarize, the inflaton field experiences quantum fluctuations during inflation. The gravitational potential is a thing that basically will source the infall of stars, right? Dark matter and all that stuff. However, the space-time metric, all right, undergoes quantum fluctuations as well, and we call those things gravitational waves. If they are quantum, you can just have classical fluctuations, traceless and transverse modes, which are just gravitational waves. And so the question we want to ask now is, what is the physical role of the B-mode polarization? What is the physical role? Does it have a physical role? Or does it just exist for the ride? And that was the question that we were asking, that I was asking David in 2005. And so just to give you a little primer on gravitational wave, so what we're looking at here is the height of a gravitational wave as it's moving through space, and it encounters a person, and the gravitational wave will stretch space in one way and then squeeze space in the other direction. It'll just be like a blob of jello going back and forth, right? So, you know, if you want to lose weight quickly, just, you know, stand in front of a gravitational wave and take a picture of yourself, but then make sure you don't get jello shot because it'll make you look like you had a bucket of ice cream for 4 days in a row. So that's gravitational waves. These are undulations of space-time generated by sources with a quadrupole moment usually, and they move just like light at the speed of light, and they have very similar physics, although a little bit more complicated polarization, and we'll talk a little bit about that as well. So what is useful here? Well, I will now, moving forward, start writing down some necessary equations because some things are more difficult to say with words. And the first thing I want to show you is that if I ignore this middle term, this is time, second derivative with respect to time, and this is space or corresponding wave vector. This is nothing more than a wave equation, and the solution for this wave equation is that I get a periodic oscillatory wave of a corresponding frequency wave vector k. But what inflation does is really interesting. The gravitational wave couples to the expansion rate. The expansion rate is exploding on you. That thing is called A. And this, when I quantize this system, I get quantum squeezing. So I get amplification of the gravitational waves due to inflation. And that's why the B-mode polarization is basically the amplitude of these gravitational waves. And they may start off very, very quantum and very tiny, but inflation itself will amplify it, hopefully to some kind of observable rate that I know that the Simons Array Telescope will hope to look for. Here's another picture of two black holes merging. There's a whole gravitational wave group here at CCA. I look forward to engaging and learning some stuff from you all. But there's a problem here. And let me state this problem as clearly as I could. In the early universe, at very, very high energies, all of the symmetries of the standard model are restored. So and the perfect cosmological principle basically states that the universe is going to be in its most symmetric state possible in the earliest stage. Which means that the vacuum, what I call the vacuum, the ground state of the system, right, will correspond to not just having matter. So we know, right, we know that in our standard model, for example, standard model of particle interactions, that theory comes for every degree of freedom with matter and antimatter. And so one big question in cosmology is we see matter around us. As far back as we can look, we see coherent structures made up of matter. It's not that we don't see antimatter events, right? But maybe Rachel could tell me, maybe one day you can look for anti-galaxies, and if you find one, I'll bow out and become a sax player for life. Yeah?
I think we know there can't be,
They can or can't?
cannot exist,
What's the argument?
because we would have, the annihilation products would affect the CMB,
Thank you very much.
or at least within our event horizon,
Did anybody ever write a paper on that?
almost certainly.
Oh, that would have been a good project. All right. So the basic point here is that let's now go back to our picture of structure formation in the early universe. The idea, the statement that inflation produces these quantum undulation, if it's happening at energies higher than the energy scale of the standard model, where it's the vacuum of the standard model, we have to explain why those undulations bias matter over antimatter. Otherwise, what you will end up doing in a theory like inflation is that you will produce both structures having to do with matter and antimatter. Now, you can then argue, well, maybe inflation does do that, but at some later time, like reheating, like some other process in between, you can do that. And people have certainly published papers on that. I myself have published papers on that. There's a reason to pursue this route because basically you get lots of free lunches here. And if nature was clever to make use of a lot of free lunches, this is certainly one way to do it. So, so the question is, how do we confront the picture of structure formation and inflation with what I call the baryon or the antimatter-matter asymmetry? Why I see more baryons than antibaryons. Okay, so it begins basically with the necessary conditions to do this was done by Andrei Sakharov, who won the Nobel Prize for Peace, actually, right? For his anti-nuclear initiatives. But he actually was also a great physicist, and he was the one that gets the credit for providing the necessary ingredients to establish, regardless of what your theory is, your mechanism, these are the necessary conditions to do. The first thing you need to do is you need processes in your early universe. So the picture I want you to have now, you're in the early universe and it's devoid, there's nothing, just empty space. There's empty space. And what you want to do is pop out of what we call empty space, or the vacuum, more matter than antimatter. Both matter and antimatter exist in this vacuum state, but you want a process that will spit out more matter, antimatter. We call that a baryon or lepton violation. Baryons is like your, protons and neutrons, and leptons are like your quarks and electrons. All right. You need something that, while that is happening, while you're producing more matter, sorry, I said this incorrectly. The first is baryon lepton violation, so you're going to produce both matter and antimatter out of nothing. But now you want to bias that. And that's where CP violation, charge conjugation, and parity violation needs to happen. While that is also happening, that has to happen out of equilibrium with the expansion rate. Otherwise, it just gets diluted away. Okay, because the expansion rate will basically make the number density decrease. And, what did I do here? Okay. So it's not just only enough to do that, but WMAP measured the ratio of the number of baryons actually from the CMB, and it agrees with nucleosynthesis and the abundance of light elements that we see today, that it's not just that you satisfy these conditions, but you need in your theory, if you're going to do such a thing, you need to spit out a number. And that number is this, 6.5. The numbers must have changed a little bit with a few decimal points, but roughly 10 to the minus 10. You need a theory to do this. Let me give you a little bit of hint. The gravity, if you look at the CMB fluctuations, that's on the order of 10 to the minus 5, right? So there's a little bit of interesting numerology that you might, some of you might be thinking about. But let's follow our noses. What we're going to do now is, let me just recap. We're looking at inflation. We're looking at the quantum fluctuations of inflation, and we're putting our focus on the generation of gravitational waves that happen for free during inflation. And we're asking ourselves, may that have anything to do with the production, with the satisfaction of the satisfying the Sakharov conditions necessary for baryogenesis? That's the question we're going to ask. And if you try to ask this question, what you find is you're going to slip on a banana peel and never get it right. And the reason why is you need new physics that happens during inflation to satisfy these conditions. And the question is, what is that new physics? And that new physics actually is a modification of Einstein's theory of general relativity. And so for those of you who care not about the equations are not necessarily important, but I wanted to show this to make, well, so many of you know this picture here, that's Chern-Simons, and this theory is called Chern-Simons general relativity. And basically what this theory is, it's basically Einstein's theory of general relativity with this new term, with a new term that's added to, there are a few of them, but the one we're going to focus on here is the so-called Chern-Simons term. It is a topological, what we call a topological invariant, right? Meaning that I can deform my space-time or whatever way I want smoothly. This term is insensitive to it, but it cares about how many holes and things like that. I had a nice lecture from Jim about that way back in 2012. And, but the thing that's really interesting is that this thing didn't come to us by magic, actually. It turns out that this term, for some interesting reason, is necessary for the quantum consistency of string theory. Another, let me say it another way. If you take string theory and you reduce it to any four-dimensional situation, this term is necessary. Okay, it is complete. It's related to something called the Green-Schwarz anomaly canceling mechanism. But it's not the only way that this term comes about. There are other, if you look at actually interesting other approaches to quantum gravity, including like loop quantum gravity, this term is also there too. So there's a kind of robustness about this term, and it turns out that this term exactly has the action necessary for these gravitational waves. So what we're going to do now is look at the cosmological consequences of inflation when we modify general relativity with this term that seems to be necessary from other theoretical motivations. But before I tell you what happens, let me tell you the basic mechanism, what basically happens, okay? I want us to go back to the Sakharov condition. And when you think about the Sakharov condition, the big hiccup many of us made when we were trying to do baryogenesis was to somehow, turn our knobs independently to get these different conditions. But what inflation does, in the presence of this Chern-Simons term, in one shot, and what I mean by that, there is something that happens to inflation that happens with the inflaton field itself that communicates simultaneously all of these conditions at the same time. What do I mean by this? The basic mechanism is the inflaton field, okay, has something called phase. That corresponds to basically how synchronized these oscillations are happening throughout your space-time. Because of that synchronization, that acts as a source, right, for the production of gravitational waves. But it doesn't just produce gravitational waves that you normally see. It produces more left circularly polarized gravitational waves than the other handedness. We call this birefringence. Biologists sometimes call it circular dichroism, but it's an abundance of one over the other. Ordinary inflation does not do this, and it doesn't do it unless you have the Chern-Simons term. That's takeaway number one. But when you produce these types of gravitational wave, where there's one-handedness over another, okay, that does something really interesting. It produces a gravitational anomaly, and that anomaly I'll talk about in the next slide is the action, is the other piece of mathematics that I know Jim is fond of, where his Chern-Simons term is connected to the Atiyah-Patodi-Singer index theorem for the mathematicians listening into this. So what happens is that you get CP violation, one of the Sakharov condition, that translates itself, or that communicates itself to actually those gravitational waves are pumping out more electrons or anti-electrons, for example. And while it's doing that, the rapid expansion of inflation keeps the system out of equilibrium. So that's the basic physics. And I like to have my little, I try to do this at home. It doesn't work, but whoever did this has got good dexterity. Okay, so the idea is that if I stir a cup in one direction, I'll see, so the chiral gravitational wave, you can think of some kind of vortical type of motion as an analogy versus the other, if I shook the cup in a different direction. And there's an opportunity here because this production of left to right asymmetry is something that I know that the Simons Observatory will be hopefully looking for. I know there are lots of technicalities having to do with systematics and all this really insane, difficult things, which keep me in simple theory land, and that I talk to Brian Keaton about from time to time. But anyway, so how does this work? I'm just going to quickly run you through these equations. The right-hand side is this Chern-Simons number, the Chern-Simons current, okay? This term that Jim and Chern wrote down. And what you see is that when this thing changes, it naturally generates the baryon asymmetry. This is a fundamental piece of our standard model. Okay, for grad students listening on volume 2 of Weinberg, he has a few chapters on all these types of anomalies and how they contribute to the standard model. But it turns out, in general relativity, the anomalies all vanish. Okay? But if you have this gravitational Chern-Simons term, and you have the action of inflation, it turns out that this term will not vanish. And why will it not vanish? And this is the important point here. My gravitational wave equation, box is just a wave equation. It's normally 0. But with the Chern-Simons term presence, there's a minus sign here. There's a minus source with an I, all right? That I basically creates a growth in the amplitude, a decrease in the amplitude. This, for the right-handed one, because of the Chern-Simons term, I get a growth of the right-handed one. That's where you see the left-right asymmetry. And anyway, this is basically, for inflation, you need these things. I told you the velocity has to be roughly a constant. These are the solutions, and it turns out that if you do all this stuff and you calculate the baryon asymmetry from this, just from this mechanism, that at the end of the day, inflation happens, you produce more left-handed gravitational waves or right-handed gravitational waves. The Chern-Simons current generates more matter over antimatter because it's tethered to the gravitational wave. And then I just go and I calculate the number produced at the end of inflation. And what you find is it doesn't get diluted, but it depends basically on this 10 to the minus 5 factor. There's a cutoff scale here, and there's some conversations about UV completeness, and we'll talk about that over dinner. But the basic point is that we can accommodate the matter-antimatter symmetry for free, just if you do inflation. One caveat: this is not limited to theories of inflation. This is a modular mechanism, so One of the things I was talking to Paul Steinhardt about is whether or not this can be accommodated in these balancing cosmologies. It's something that somebody should look at. Okay, cute, but can we test this idea? And I'm just gonna basically point you to some papers that looked at these things. David also worked on this with Nico as well. Yeah, so just look at those papers. We wrote a physics report in 2005 called Chern-Simons Modified General Relativity. You can take a look at that. But the answer is people are on the hunt to look for these circularly polarized gravitational waves in many different windows. Now, another interesting thing too is that if you did have the black actually represents the power spectrum of circularly polarized gravitational waves when you have one over the other versus the normal B modes, and it's about an order of magnitude larger, okay, for a TB. So that's interesting, and I know that Komatsu is interested in this as well. And of course, the big one, the big gun is the Simons array telescope. That's the director, Brian Keaton, this will be recorded so you can freeze a frame and look at all these specs there. Now, the last part of my talk, and how much time do I have accounting for my, Mr. Chair?
I would say you'll still have 15 minutes.
Oh, perfect. Okay, I can slow down now. All right. Clearly what we're looking at here is a rotation curve of a spiral galaxy. It's a cartoon. This is supposed to represent some real data, but the basic point is that we see that to accommodate this flattening of velocity, we need dark stuff. 85% of it is missing. All right? This is one aspect of dark matter. Right? So here's a little cartoon of a spiral, and we have this profile of a dark halo of this dark stuff for which we don't really know, aside from the various observations, what its identity is and the underlying physics of this dark matter. And so we're gonna now ask the question about the dark matter. And the reason why we want to ask the question about the dark matter is because we see the evidence of dark matter in the CMB fluctuations. And it's just a natural question to ask that if you, well, let me get to the next slide. So going back to coincidences, David, I forget when the WIMP miracle and WIMP coincidence came on the scene. I think yeah.
In the 90s, I think.
Well, we knew about it in the 80s.
You knew about it. I think you made an observation as a grad student about it, right? So this miracle is amazing. You see this coincidence, right? That it turns out that if you look at the annihilation cross-section necessary to get the right abundance of dark matter, if it happens to be electroweak scale, it works. And so you then say, oh, wow, maybe there's a chance that this has to do with electroweak physics. They went looking for it using that channel, that modality, and they found, so far, they're still on the hunt for it. And so David was actually visiting Providence, coming through Providence. We had dinner at a Malaysian restaurant. And I said, David, I'm desperate. I don't know what to do now. Can you if there's something about dark matter, is there any other coincidence? Because I got, give me another coincidence. And he said, oh yeah, there's another one. And it's this one. Why is it that the critical density, so with dark matter, 5 times that of the baryonic matter? Why are they kind of proportional to each other? Why, it could have been one is 10 to the 12, whatever. Why this type coupling? But it's not just that. If they correlate to each other that way observationally, and they don't interact, how could they know about each other? That's the puzzle here. If you take that observations and say, maybe I can try to find some physics to explain that, well, good luck trying to do it if they don't talk to each other. But if I play some numbers here, this is nothing more than the number density, roughly times the mass of the baryonic matter. And guess what? The number density has to be explained by baryogenesis. So if you were to maybe, relate this to this, then you have to maybe talk about dark genesis, the genesis of dark matter. So we said, well, let's talk about this. And I went down to CCA and visited them for a couple of days and went back to Providence. And on the Amtrak train, I said, oh, wait, this is actually interesting. This is like a little gift because, the person that told me, hey, go work on this stuff, it turns out to be the mechanism that can do it. So we went back to the drawing board and we wrote this paper. Well, we did calculations, me, Evan, and David. And we found that actually the Chern-Simons theory provides exactly the same mechanism to generate the dark genesis. So if you explain the same ratio, the same amount of abundance, you're naturally going to get the same ratio. You have to get the factor of 5, but let's, we're theorists, so let's talk about the factor of 5 tomorrow. Or hamburger today. So we can do this. But I want to just back off a little bit here. Many of y'all heard about the multiverse and all this stuff, right? This is not the multiverse of inflation, where you have different pocket universes. No, this is the multiverse of dark theories. I actually want to give credit. I got this slide from University of Amsterdam. Okay, and so every pocket here represents a different dark matter model. Okay, and so the game of dark matter theory building, model building, can sometimes appear to be quite ad hoc. Here's my dark matter model. You go to the market. Okay, who's this better? Survey says. All right. So how do we distinguish them? And that was something that we worried about. We didn't want to just say, here's just another ad hoc dark matter particle in theory to add to the multiverse. Well, it's really interesting. We got stuck on the calculation, and it turned out that Ed Witten came to the rescue. Witten wrote a paper in the early 80s called they call it the Witten anomaly now. It's an SU2 anomaly. And it has to do with, again, something to do with the Chern-Simons term. And well, it turns out, let me just say what I'm saying. One of the things I didn't say in this talk, I wanted to keep away from it, is that when you violate the current or the number density of something from its vacuum, you're talking, and if that is a quantum process, that is what we call an anomalous process. Quantum mechanics usually doesn't like it. It violates a probability current violation. You have to cancel it. And that is a very tricky dance. And it turns out what Witten showed is that acting in this mechanism that we are looking at is actually a criterion, a very stringent criteria to not make your quantum theory go bad and nuts on you. That's doing all this stuff. Otherwise, it's sick, it's not unitary, all this sickness. And it turns out that puts an immediate constraint on the theory itself. So we can't have an ad hoc theory here. It turns out that you can't just have, what it tells you is that the theory of dark matter is a dark copy of the weak interaction. An SC2 theory, it doesn't have hypercharge, it doesn't have dark electric charge, it's just pure weak with fermions. And the fermions live only basically in 2 flavors and SC2 doublet. That's it. That's coming from these anomaly canceling constraints that Witten spelled out. And these things also, another prediction from this, so again, the theory predicts the model in this case. This mechanism constrains it, whether you believe it or not, this is the game we're playing, it tells us that basically, another thing is that these particles are not dark particles, they're not WIMPs. What are they? Well, we have to now look at the phase diagram of this theory, which has been looked at on the lattice. And it turns out, and this is a typical fact just about good old-fashioned QCD, that when you go to high number densities and low enough temperature, you are living in a condensate state, meaning a coherent, phase coherent state where your quarks pair up like a Cooper pair. to form a superconductor or a superfluid, depending if it's charged or not. So this dark matter particle is predicted based on the early universe dynamics, because we trace this evolution after inflation into the contemporary universe. And when we look at the freeze-out status of this, it basically pins you into that the dark matter is a superfluid, but not a bosonic superfluid like an axion, but a fermionic superfluid. So, upshot is, in my story, you get the baryon asymmetry, and you get this dark symmetry where the dark sector is a copy of the visible weak sector, but the state of this thing, as it cools off and becomes collisionless and cold, becomes, its ground state is that of a stable superfluid. A fermionic superfluid. That's very important because the excitations of its spectrum will be different than the bosonic case. And so I just want to kind of summarize what we're talking about here is baryogenesis and dark genesis. At the top here is maybe time going down to the present moment. We have inflation plus circularly polarized gravitational wave working together. It gives both visible and dark matter asymmetries, but the dark matter, right, instead of behaving like particles, end up in a superfluid, fermionic superfluid state. And basically, if you look at our paper, you can look to see the details. So why don't I talk about future directions? So there was a beautiful paper by Nassib, is that the right pronunciation? Lasante and Belukharov. Mariangela gave a colloquium last year at Brown, and we got to talk about this. But this statement that our own Milky Way is not is not in equilibrium opens up a kind of a Pandora's box, basically, for the possibility that substructure or the dynamics of substructure could be something to pay close attention to. Okay, and so we were motivated by this idea of substructure, because one of the things about superfluids, we'll talk about this in a second, we can write down the theory. We can, and this was written down by Wayne Hu. Wayne called this fuzzy dark matter, and Wayne was led to this for different reasons. He was trying to ask this question that large n-body simulation with NFW profiles lead to cusps at the center of galaxies, but we don't see that. And so Wayne tried to understand, well, how do we keep not throw the baby out with the bathwater? We have dark matter. How do we prevent the dark matter from doing that and while we remain in a halo? And he used quantum mechanics, the same thing that keeps the electron in a low stable orbit. If it has a de Broglie wavelength associated with its mass, if it's light enough, it will keep itself away from the center due to the uncertainty principle. So the superfluid picture came about that way. We came at it in a different direction, and that's kind of interesting to me. But we actually have the equations. Wayne wrote these equations down many years ago. And it's basically what we call a Newton-Poisson equation. We have the Schrödinger-Newton equation. We have a Schrödinger equation. We can't no longer use classical physics. We have to use a Schrödinger equation for the condensate interacting with gravity in the vicinity of your halo. And there's some work done by Hui, Ostraker, and Witten, and Tremaine, and other people at the CCA. I know Philip Marx has been working on this numerically along with others. Apologies for not, in this colloquium, mentioning all the names. But here's what we found in our system. We went and we tried to solve this. We worked with an applied mathematician. So yes, I do like talking to people in other fields and writing papers with them when possible. And we found actually new solutions, new stable solutions of these types of interacting solutions. And the applied mathematician provided some proofs that these solutions were for real, mathematically. And what we found is basically stable dark disk-like substructures with families of disks, including different orientations, which may or may not live in the plane of the galaxy. They could even be isolated, like little disk dwarfs, okay? But these solutions, finding a solution to the cubic Schrodinger equation in the presence of a hyperbolic, the Poisson equation is not trivial. And the fact that these are non-stable solutions, and you get a family of them, I think is something to pay attention to, theoretically at least. And I'm not gonna jump into this, but my graduate student, this is mainly work pushed by my graduate student, Michael Toomey, who is like our local machine learning expert at Brown in our department, did a classifier, tried to classify basically the presence. Basically what we did basically was, this is, I didn't cite the paper here. We basically said, let's take a gravitational lens, okay, say from Hubble, and we're gonna look at basically, if I put 1% in my halo of an overdensity that corresponds to a disk, it's 1% of it. Can a neural net, can I see this in a lens? And so this was a perfect problem for CNN, and so this is the result we got from that. It's a paper we published in App Journal. So we get near perfect classification, and the detection threshold is 1% of the halo mass. And so if you're above 1% of the overall density, it starts at 95% confidence. Okay. Anyway, so these are the AUCs. And this is now a work in progress with Evan and David and myself. And this is a bit kind of crazy, but why not? Okay. We're in crazy times. And so, there's a famous song, you're never gonna survive unless you get a little crazy. So the idea here is, take a neutron star. It's in a condensed phase. It uses, QCD. Take a neutron star and make the neutron star as big as a halo. So you do the same physics so that you keep the necessary pressure, right? To keep the density and the pressure, to keep the condensate, keep you in the state. The only thing you have to play with in your theory is the QCD scale, as well as the densities and stuff, but let's just focus on that. That means that my dark QCD theory, if it was sub-electron volts, in the order of sub-electron volts, not like ordinary QCD, which is a million electron volts, if you scale it down, you basically find that the core of a halo in our model looks just basically like a neutron star. So that means we could import a lot of the physics. We can go talk to our friends that work on compact objects and neutron stars to maybe think about, I'm now talking about in the vicinity of the superfluid state. And this is now the fermionic superfluid state. So this is stuff that, we are now currently looking at and talking about, and I look forward to talking with many of you at the CCA and at Flatiron about this and learn things from you all. So just to conclude an outlook. So we linked the early university origin of baryon and dark matter with the same mechanism. That's our tail, okay? I'm from the Bronx, and we have a saying, man, if somebody's telling a mistruth, we say, man, you're telling DuckTales. It's like this cartoon we used to watch when we were kids. I think I got some friends up in the Bronx actually watching this. So we got some.
That's what they're saying to each other. They're like, oh, he's telling DuckTales.
So there's a possibility to test maybe this with substructure, because these models also predict substructure. It also predicts vortices and potentially tangled vortices, and I have no idea what that would do to streams and things like that. It might be that once a clever enough astrophysicist sees this, they'll be able to find a really smoking gun way of just ruling a theory like this out. Okay, so that's why I do theory. I don't do theory just to be right, but to be wrong. I can still buy time by coming up with more wrong theories. This will require computational oriented projects, and I look forward and my students to many discussions with you all and this year. Thank you very much.
Thank you so much, Stephon. So now, please raise your hands if you want to ask questions to Stephon regarding the talk. So I see Richard.
Yeah, thanks for the nice talk, Stephon. I'm wondering if we can make the concept of baryon asymmetry a little bit more quantitative. So we observe different amounts of baryons versus antibaryons, but we still have maybe a few anti-hydrogen molecules there. So for the people saying that there wasn't any structure in the antimatter, there you have it. And of course, it seems to our viewpoint that omega baryon and omega dark matter are close, but if we rely on just our qualitative intuition to say that these things are close, we may be missing other similar things that we don't really view as close in the same way that this factor of 5 for omega baryon and omega dark matter are heading us to. So is there any way that we can make a fundamental scale or a fundamental comparison saying that these are close when we're talking about these types of asymmetries versus these aren't close?
David looks like he wants to give the answer. I mean, from what I'm hearing from you is that, first of all, the observation of the matter-antimatter asymmetry itself, right? That number I gave you was read off from the WMAP data itself, right? That's what the data is telling us, okay? What you're talking about is maybe in the contemporary universe, we might see events of antimatter, things like that. That, even when you account for that, it doesn't add up to the amount necessary for nucleosynthesis. That's my answer, David. What's yours?
So, I mean, I was just going to comment on that there are that factor 5 coincidence. You say, well, what other things are kind of like that,
yeah.
right? The energy density in neutrinos today is also, just a factor few off the energy density in matter. And that's another one that's depending on the neutrino mass, just to add to your list.
Yes.
So I had a question.
Okay, yes.
So on the baryogenesis,
Yeah.
you had an equation back there relating it to the Hubble constant, H over m Planck, and that's the Hubble constant during inflation.
Yes.
That relates directly to the amplitude of gravitational waves.
Yes.
So if this mechanism is responsible for baryogenesis,
Yes.
it looks like you have a pretty direct prediction on what the gravitational wave amplitude must be.
Yes.
What is that number?
But David, what you basically stated was the conclusion of that PRL we wrote about this mechanism, and we found that it has to be, it has to be R, a large R, but not ruled out.
Well, but
by Planck.
But not ruled out by Planck. But it looked like it's if we knew R was what with Simons Observatory.
Yeah.
One of the targets is to be able to say either we see gravitational waves or R is less than 10 to the minus 3.
Good. Then
That looks good enough. If we don't see it, this mechanism's ruled out.
That's right. So Simons array will actually, you can say that one of the things to add to the list of Simons array, it's a probe of models of baryogenesis. And that should be on the wish list. Yeah. If you don't see, or if you see ridiculously small R or something that's constrained away to be whatever, then models like this, where this is, by the way, this is very generic. These are models of inflation that do this. We wrote the first paper on that, right? And then many others came after that. It will basically knock many of those models out.
More questions for Stephon? In the meanwhile, I want to say that Mordecai posted a reference on matter-antimatter constraints, so
Thank you very
I'll
much.
pass it
Thank you
along
very much.
to Stephon later.
I have a very simple question. So when you mentioned that primordial fluctuations can perturb the slow roll potential for
Yes.
the inflaton,
Yes.
and they would also cause the gravitational waves. Is this a necessity? Like, could you have perturbations that don't have a quadrupole moment and so don't generate any gravitational waves?
Well, yeah, that's a good question. I mean, typically we say, right, we typically say that all models of inflation, right, will produce these tensor perturbations because we're relying actually on the quantum fluctuations of space-time itself, including the gravitational potential as well as the tensor part of G mu nu. Okay. Now, does it mean though? Yeah, that's a good question. That's a good question. I mean, it could be that there are theories of general relativity in the quantum gravitational realm that naturally will suppress tensor modes. That's a good. I mean, it's a good question. Okay. Like for example, asymptotically free theories of gravity, right? Where in the UV you do suppress certain modes of the graviton. Might be one way of doing it, but it's a good question.
Okay, so I don't see any more hands. So we're gonna thank Stephon again for this great talk. Thanks everyone for tuning in.